Freshmen? Sophomore? Any seniors? Oh, very good. Okay, that's good. You want to tell us perhaps why you're taking this course?
I studied physics originally, and we don't get enough training in computer, like in coding. It's just a very valuable skill, especially if you want to do physics after graduating.
Yeah, absolutely. Very good. Great. How about somebody who's planning a major in a CSE major? Somebody want to explain? Yeah.
With CSE, you can do any field that you want. So, like, it integrates with every field. So I can really do whatever I want when I graduate.
There is a fair amount of truth in that. Right, yes. I mean, you need some domain knowledge, but yes, it is valuable in just about everything. Yes. I don't know. What do you want to hear war stories? What do you want to hear? Okay, so when I finished my PhD, I went to work at Bell Labs, and my first boss, I want a browser.
There you go.
Okay. No, not that, George. The other George. My first boss was George, who we termed George Bureaucratic Commando Smith. So at one point, one of the guys had put in an order to have some plugs moved in his office. Months later, still didn't happen. So George walked in the office, took a paper clip, unfolded it, stuck it in the plug, and said, "My goodness, that is a clear safety hazard, and as departmental safety representative, I am required to report this." So he wrote up the form. Next day, boom, moved. Okay, that's problem solving, folks. That's how you get a Nobel Prize, is that level of creative problem solving. Okay, let me tell you that computer science is hard work. Okay, computer science is not, using computers. It's designing computers, software, hardware, systems that people depend upon. Even a video game people depend upon, right? They're paying for it. They want it to work. Right? A lot of the work that we do directly affects people's lives, and a fair amount of it is in critical infrastructure and safety critical systems. Okay? We have an obligation to do a good job, and doing that good job just takes hard work. Okay? But, I've been doing this for a long time. You rightly pointed, there are all sorts of opportunities in computing, more every day. Okay, so perhaps we can have more conversations in the future about computing. I'm going to try to meet with students in various forums and various venues, and overall, I will see you around campus. How's that? Good. Thanks.
And the way that you get involved in a lot of campus stuff, especially with the department, is you pay attention to the letter that you get every Wednesday. What was that called? Bits and Bytes. Excellent. Hopefully you got one today, because they are looking for ambassadors. They are looking for, I think that there are 3 or 4 job opportunities that they're advertising. And of course, if you like running, then we are going to be running on the 27th, which is not this Friday, but next Friday. If you want to come out and run a 5K with the faculty around the, just 3 of us. We couldn't get all the faculty to agree to this. So 3 of us will be running around campus. It's a nice brisk 5K, weather pending, of course, next Friday. So make sure to pay attention to Bits and Bytes because there are a lot of opportunities in there. And getting involved, another one that I was trying to remember was CSAB, which is the Student Advisory Board. You can go ahead and get involved with that. It's not exactly student government, but it's kind of like a student government for the department itself. Okay? All right, so what I wanted to do with our time today, we will move on to the next topic, but before we do that, I wanted to write a few more examples. Like you got, especially since you got some practice yesterday in lab, I want to do some more examples writing loops. And the first example that I want to do in class is what's called the classic Fizzbuzz program. Now the Fizzbuzz program was popularized, not created by, but popularized in this article from 2007, which was part of your required reading a couple weeks ago. And the author of this is Jeff Atwood. Does anybody know who Jeff Atwood is? All right, well, if you type in a question about coding, you type in, well, how do I do this in C? What's probably going to be the website that comes up with the #1 hit? Stack Overflow. He is the founder of Stack Overflow. And he runs this blog, and this is a great article back in 2007. Basically, it's a bunch of employers lamenting the fact that none of their or 99% of the people that come to them and apply and say, I've got this many years of experience in programming, they can't program. So they are truly imposters, or they're lying or something, but there's just something there that just doesn't click. And the way that they've dealt with this in interviews, of course, you can have technical interviews where you're grilled. I interviewed at Google many years ago, and it was an on-site interview. I was grilled for 6 hours straight by 6 different people, 1 hour each, on technical stuff, like write an algorithm to do this, analyze this algorithm. It was a grueling interview, but hopefully you'll never have to go to a grueling interview like that, and that's a thing of the past. But one thing that they do in a lot of interviews is just program me something small. And according to these testimonials from these industry people, this simple Fizzbuzz program is able to filter out 90% of all the candidates. It's such a simple program that anybody that even has gone through 4 weeks of a CS1 course should be able to do it, because it involves simply just conditionals, loops, or it does involve a loop, basic variables, and basic input and output. So everything that we've covered up to this point, that's all that is required. And there are testimonials in here that do it in any language that you want. Do it in language that you claim to have 10 years experience in. And some testimonials are that even senior programmers take more than 10 to 15 minutes to actually write this. We might take 15 minutes here because, of course, I'm going to interject with, let's do it this way. Oh, no, it didn't work. Why not? And then let's go ahead and try it a different way. But here's the basic statement of the program. Let's see, 100. Where is it? All right, here's the program statement. Write a program that prints numbers 1 to 100, but for multiples of 3, print fizz instead of the number, and for multiples of 5, print buzz. So it should print 1, 2, 3 is the first thing that is a multiple of 3, so we'll print fizz. 4, 5 is the first thing that's a multiple of 5, so we'll print buzz. 6, do we print 6? 6 is a multiple of 3, so what do we print? Fizz, right? And we continue like that until we get up to 100. What's the first thing that we print Fizzbuzz on? What's the first number that's both divisible by 3 and by 5? 15. So there's a little bit of tiny little bit of mathematics involved in this, but it's certainly something that a CS, somebody who has gone through 4 years of a CS curriculum should be able to handle. So we're going to go ahead and do this. And by the way, just in case you think that this is hyperbole, I used to think that this was hyperbole until I started giving this exact problem in this course. Just as an example, last year I probably won't do it again because I'm telling you this story, but last year I gave Fizzbuzz as a midterm problem. 40% of the class could not do it, even though we had done it in class, even though I had mentioned it, even though it was an open book, open note exam, right? So there's just something about it that separates the people that know what they're doing and understand, and those that don't know what they're doing. Right? So we're going to prove today that we know that what we're doing, right? Or at least I'm going to try to prove that I know what I'm doing. Right? Okay, so let me go ahead and increase the size here. Something a little bit more manageable. So again, we're going to print numbers 1 to 100, except if it is divisible by 3, print fizz. Right? If it is divisible by 5, print buzz. Right? And if it's divisible by, and if it's divisible by, if by both, print fizz buzz. Okay. Again, that's just me writing the problem statement here, so that we rewriting it so that we don't lose the forest for the trees. Help me out. Are we going to want to use a for loop? Is that more natural, or are we going to want to use a while loop? Which one is more natural? For loop. Why? Because I know that I'm going to be printing 1 up to 100 and sometimes something else. But I know a priori. I know up front that I'm going to be doing this for 100 iterations. So I agree. Let's go ahead and do it with a for loop. Doing it with a while loop is perfectly acceptable, by the way. Any for loop can be rewritten as a while loop and vice versa. It's just one is more natural to write and more readable to write than another. So I'll go ahead and start with an index variable here. Where should I start? Should I start at 0? I could, but I'm printing numbers 1 to 100. So where should I start? Probably at 1. Semicolon. I is less than 100. Is that right? You want to include 100, so you'd be off by 1 there. Right? And we'll go up in increments of 1, because we do want to consider 1, 2, 3, 4, and only if it is divisible by 3, then do we not print the number. We print something else instead. So how do I test whether or not the number I is divisible by 3 or not? I, what was that integer division? Mod, it's called mod modulus, right? And it's the percent sign. And if I divide it by 3, I get a remainder of either 0, 1, or 2. Which remainder tells me that it's divisible by 3? 0. Right? I'll print fizz. And I'll end the line, of course, to make it more readable. Else, if I mod 5 has a remainder of 0, I'll go ahead and copy pasta buzz, biz buzz. That's why you don't copy pasta, right? Else, I'll go ahead and printf the number, %d, and the line I. Right. Now, is this a complete and done solution? Let's go ahead and test it. There's 1, 2. Fizz is the first thing that's divisible by 3, so that looks good. 4, buzz, that's instead of 5. Fizz, again, 6 is divisible by 3 because 2 times 3. 7, 8, neither one of those are divisible by 3 or 5, so this is looking good. Are we done? No. If I jump down here to 15, what do I see? I get to see fizz. What should I see? Fizz buzz. So let's go ahead and add another condition here. If I mod 3 has a remainder of 0, and I mod 5 has a remainder of 0, then it's divisible by both, right? And in this case, I will print, not Fizzbuzz. I want to make sure that I maintain my else condition here. Fizzbuzz. Right, and end the line. There we go. Let's try it again, see if that fixed it. Come back up here to 13, 14, 15. It didn't work. Why? Yeah, anybody. Go ahead and yell it out. Okay, that's not going to work, I guess. So, what? It already satisfied the if condition for 15. I don't have enough fingers, but 15, right? That's divisible by 3. Remember, if, else if is all mutually exclusive. The first one that gets evaluated to true, that's the one that executes, and that's the only one that executes. So consequently, when it's 15 and it's divisible by 3, it only prints fizz. So where do I need to put this condition in order for this to work? I need to put it at the start, right? There we go. That is my most specific condition. Else if. There we go. Fixed all the syntax. That's good. That is the most. So the takeaway from this is if you've got a series of if else, the most specific condition needs to go first. Then more general until you get down to the else condition. The else is everything else, right? That's the most general that you can get. So let's see if this works now. Great, I think we passed our interview. It goes up, well, does it go all the way up to 100? What's the last thing that it should print? Is 100 divisible by 3? Nope, but it is divisible by 5 because 5 times 20. And so it prints buzz at the end, right? And it printed a number for all the others, right? So it looks like we passed our exam. Are there any improvements that we can make with this, though? All right, what's one? Suggest me one. Yeah.
Equal 0, but you probably just make it evaluate by putting a not in front of it instead.
Oh, okay. You could do something like this. Because if it's the result is 0, it'd be false. So you'd want to flip it and do something like that. Right? That'll lead to fewer characters of code, but in my which one is more readable? Line 14 or line 16? 16? 16 votes. All right. Line 14 votes. Oh, you're not even going to vote for your own idea? Okay. All right. So one of the takeaways is shorter code is nice. Simpler code is good in general until it gets too short. If you shorten the code down so much that it becomes unreadable or it becomes more difficult to read, then you're not saving anybody any time. In fact, you're costing time in maintenance. Remember, it's Goldilocks. Not too long, not too short, just right. Keep it simple, but don't keep it so simple that it loses all meaning and it's no longer legible and readable and understandable. There is a type of coding game called Code Golf, where you're given a program to write, say a Fizzbuzz program, and you have to write the smallest program that will produce that output. You could, of course, do simple tricks where you get rid of all the white space, right? Now it's all on one line, one really long line. But then you can take out this or this character. You can shorten it up a little bit more by doing that trick. And it's called Code Golf. Why? The shorter one wins, just like the fewest number of strokes in golf wins. And that's a game that you can play, and there are plenty of things that you can do online, and you can enter Code Golf tournaments if you want to. But real code needs to be more maintainable and readable than it needs to be short. So look for that Goldilocks zone where it's not too short, it's not too long, it's just right. All right? Is there another improvement? Yeah. Sorry, say again? Oh, yeah. If something is divisible by 3 and 5, then what does that mean it's divisible by? 15. Right? I could change this to one check. If it's divisible by 15, then print Fizzbuzz. And you can see that it leads to the exact same thing. 15, 30 would be right here, and then 45, et cetera, et cetera. So I changed it. I would argue that is a little bit better because now it's actually more readable. Right? It follows the KISS principle. Keep it simple. Right? So you can do a whole bunch of other things to improve on this, or to get it down and simpler. You could make it so that it's not if else if. If it's divisible by 3, then print fizz. If it's divisible by 5, print buzz. Without the end-line characters, and then by printing fizz buzz, you'd actually get the fizz buzz out of that. You could do tricks like that, or you can go the opposite direction. And as a joke, fizz buzz Enterprise Edition. So when code is over-engineered, when there are a million lines of code to do one simple thing like Fizzbuzz, that's when you've got enterprise-y code. And a classic example here is somebody, as a joke, they put together an enterprise-level Fizzbuzz program. This is all in Java. So take a look at the source code here. First of all, there's a bunch of testing code, which is good and nice. But take a look at the number of files we have here, just to print out 1 to 100, except for those conditions. We've got printers, parameters, arithmetic, loop, factories. We've got hundreds of lines of code here. I don't even know if we can. Let's see. We've got 29 pull requests. They want to make it even more complicated. But you've got dozens and dozens of classes in this Java programming language just to print out 100 numbers or strings, right? And it's a joke. It's going the opposite direction of code golf. Code golf, making it insanely small so that you can win a contest of code golf. The other way, making it insanely large to make fun of enterprise-level software that is over-engineered, overly complicated, when all you need to do is these simple lines here. Right? So I'm going to go ahead and cut and paste this, which should and include it in the notes, which should be a strong hint here that it's probably not going to be on your midterm. Right? All right. But there will be something similar to that, right? There's something just as simple as Fizzbuzz. One last exercise that I want to do here is going to be very similar to what you're going to be doing in your hack on Thursday, tomorrow, is we're going to write a program to project the total earnings in a savings account. This is a simplified version of what you're going to be doing tomorrow, because tomorrow you'll be doing a 401k savings program. This is just one simple savings account with a fixed APR, that's annual percentage rate, an initial balance, and a monthly deposit over a specified number of years. So the scenario here is, say that I've got a savings account with $1,000 in it right now, and it pays 5%. All right, no way is it going to pay 5%, but let's just go ahead and assume that. And each month I make another deposit. Say I make a deposit of $100. Okay, so by the end of the year, end of year one, how much would I have? Well, I'd have the initial $1,000. $1,200 that I've deposited, $100 a month, so that's $2,200. But I'd always also have interest, monthly accrued interest. Not 5% each month, but 5% divided by 12 gives me a monthly interest rate. And when I do that, then I multiply the current balance. I don't get paid based on the balance a year from now. I get paid based on the current balance. In the first month, I get paid $1,000. Or I get paid 5% divided by 12 times $1,000. Right? Now, all of that was really hand wavy. So what I'm going to do is I'm going to switch over to the overhead projector here, and we don't have. I guess there is a whiteboard over here, but I'm going to what's called whiteboarding. Let me switch over. Here we go. .cam. There we go. All right. So here's my, to understand this, what I'm going to do is I'm going to do a simple example on paper. And this is exactly what you should be doing when you collaborate with people. Now, a piece of paper and a pen, that's a single person activity. For it to be multi-person activity, you need to go up to a whiteboard. One person writes, maybe then another person comes up and writes, and because it's your way of communicating. You're communicating back and forth, you're whiteboarding something. Right? And by the way, in the interview, a technical interview, that's basically what you do. You whiteboard something. Whiteboard me, draft a design up on the whiteboard of this system to do this thing over here. Okay, it's an excellent way of understanding a problem because it forces you to write it out. It forces you to present it to another person. Another person has to understand your understanding of it, and that way you can come to a consensus on you're misunderstanding this one point, and I'm misunderstanding. The other person says, well, you're misunderstanding this point, and so you come to a consensus. Right? So here's the idea: say that I've got a $1,000 initial balance. Right? Here's month one. After the first month, how much interest have I accrued? Well, currently, the balance is only $1,000, right? So let's keep track of the balance, too. $1,000, right? And the monthly interest. So at 5%, how much am I making? Am I making 5% of $1,000 is going to be $50? Am I going to be making $50 in 1 month? This is an APR, an annual percentage rate. I want a monthly percentage rate. So 5 divided by 12, and by the way, 5% is 0.05. What is that going to be? I'm tempted to up this to 6 so I don't have to do the math in my head. This is just arithmetic, though, right? So, let's see. I don't have a calculator now. Anybody yell it out if you got it. 0.00 or 0 what? There we go. All right. So my monthly interest is actually going to be the monthly interest rate times the current balance, which, since it's $1,000, I can do that in my head. That's only going to be $4.17. Why 17 cents? It rounds up, right? Now, if it were less than half penny, then it would round down. Now, real financial institutions have much more complicated rules for rounding stuff, but we'll go ahead and stick with just regular old rounding, okay? So what's my new balance? Remember that it's $1,000 plus my interest here that I've earned, plus I'm making a monthly deposit of $100. So I should get $1,104.17, right? Now you do this for several months, and and not only do you have now an understanding of how it works, but you also are going to get a nice little test case. A test case that you've worked out on a piece of paper that you know, you cross your fingers and make sure that you didn't make any errors, but you have a reasonable expectation that this is all going to be correct. Let's go one more month here. $1,104.17. And by the way, we're whiteboarding right now because you can see it. So yell out any errors. And of course, I was asking for you to do the calculations for me as well. So what's the monthly interest now? What is 5% divided by 12 times $1,104.17? $1,104.17 times 0.05 divided by 12. I've got $4.60. Does anybody else have better? Or confirm that at least? Yes, good. All right. All right, so how much money do I have after the second month? It's going to be $4 or now $8.77, and then 1,100. But remember, I've got that monthly deposit that I'm committing to $100 a month. Maybe one more month here, so that we that we know we've got at least a little bit of testability here. Right? 77. What's my interest rate going to be now? Or what's my earned interest going to be now? $5 and what? $5.04. And you rounded that correctly, hopefully? 5.04. Okay. All right. I think so. All right. So $1,313.81. Right, there we go. ... If I wanted to do this for the next 10 years, how many months would that be? 120, right? So here's my savings table, my savings amortization table. I wonder how much money I'll have at the end of 10 years if I commit to this kind of savings, okay? Now, again, this was whiteboarding. It was not on a whiteboard, but you get the same idea. At the end of the day, you'll have a ready-made test case that you can now, when you write your code to do this, you can go ahead and verify that it's correct. But not only that, but this process of working it out mapped out a loop for me. What did you do? Well, for each month from 1 up to 120, you had a current balance. You multiplied that by the monthly interest rate to get the monthly interest. That monthly interest then was added plus the monthly deposit, giving you a new balance for the next iteration. Repeat that process over and over and over again until you get down to the end. So let's go ahead and write this program. All right, let's see. Back to this. There we go. All right. So I'm going to need some variables first. I'm going to go ahead and create variables for the current balance. I don't know, double. And why am I choosing a double immediately? You can have pennies, right? So here's my balance, my current balance. Right? And let's say I'll hard code the values here. Normally I would read them in from the user as command line arguments, but I just want to get this program working. So I'm going to go ahead and hard code that the same test case that I had over here. $1,000 initial balance. My APR, I think we said it was 5%, right? And what was the other thing that I had? Monthly deposit. There we go. And we committed to $100, right? There we go. A very modest savings, right? Although 70% of Americans would not be able to keep this kind of savings, right? Unfortunately. All right, so we've got these three values here. Suggest to me, do we need any more variables? If we need any more variables, we'll come back and take care of that later. What kind of a loop are you going to want to do here? A for loop or a while loop? A for loop? Okay. Why a for loop? For it's going to be 12 years or 10 years, 12 months a year, 120 total, right? So that tells me that I need another variable. What variable do I need? Num years, right? And we said that we were going to commit to 10 years, right? Now, of course, you could change this so that it's 10 and a half years, which would be, 10 years and 6 months. But I don't know what 10.51 years is, right? That's going to be 10 years, 5 months, and a couple of hours or something like that. So I don't want to have to deal with that. I'm going to go over it only in monthly increments, which is how a savings count actually works, okay? So for int I equals something, I is less than or equal to something, maybe, I plus plus. What am I going to be capturing here with my I? What do you want to capture? The what? Well, I'm capturing the current balance here in this variable already. What am I going? Remember the table here. What did I have each line? Each month. All right. So I here is going to capture the month. So I should start it at 0. Did I write a 0th month on this? No. I started at 1. I went up to and including 120, but I don't want to always just do 120 months. I don't always want to do 10 years. So I'll go ahead and go with num years. Is that correct? No. This would only go 1, 2, 3. This would be like annual, which would be a terrible savings account. They only pay you once a year for your interest. It means it's not compounding monthly, which means that you're missing out on, well, with a balance of $1,000, you're missing out on pennies a year, right? But if you've got a much larger bank account, then you're missing out on hundreds of dollars a year. So it's num years what? Times 12. That's how many months this is. If you want to, you can take this and put it into another variable, right? Like this. Which one's more readable? Tell me. No, to change this to months, to put it into another variable, and give it some white space here. Which one's better? Right. How many votes for this? What I currently have. All right, it looks like more than half. Votes for the other. Okay, all right. That one's in the gray area where you can debate about style all you want. You can get into internet slap fights if you really want to over that kind of stuff. Whatever. I'm going to go ahead and go with this because that's what the majority of you said. Okay. Again, that's in the gray area where it doesn't really matter. Right. Now there are certain things that do matter, like not being consistent about your style at all. Using completely stupid variable names like my variable 1, my variable 2, et cetera, et cetera. And there are completely smart things like the opposite of those things. But everything in between, you can go ahead and debate about that all you want. Right? So months. What am I going to do here? What did I do on this? I printed 4 numbers. I printed the current balance, the month, the current balance, the monthly interest rate, and then, or monthly interest earned, and then a new balance. So one thing I want to do is print out I want to calculate the monthly interest, right? So let me go ahead and do that. Monthly interest. What was that equal to? That was equal to the current balance times the APR divided by 12. Now, do I have an issue here with integer division? Is APR an integer? Nope. So at least one of them is a double. I could be really pedantic about it and make sure that it's 12.0, right? But I generally don't have an issue here. Do I have an issue here with order of operations that I should put this into parentheses instead? You don't have to, right? Because it has the same order of precedence left to right. PEMDAS, right? I never remember that one. Or you could take this and put it into a variable. Right? There's the APR. If you want to, you can immediately create a monthly interest rate. Right? Not monthly interest, because monthly interest, that connotes dollars. Right? Monthly interest rate, I can go ahead and save that off into a variable. And now I understand what I'm doing each and every single time I'm doing this. Right? I'm multiplying by the monthly interest rate rather than, oh yeah, that was an annual percentage rate. I need to divide it by 12 every single time. Right? So yet another variable if it's more readable. Right? Okay. There's my monthly interest. I'll leave it like that for now. I add that to the current balance, right? Current balance is, current balance is going to be equal to the current balance plus the interest that I just earned. Oops, there we go. Is there a more compact way of writing that? X is equal to x plus 10. I could just write that as plus equals. Right? Remember that syntactic sugar. Plus equals allows me to not have to repeat that variable. Write shorter code. Shorter code is generally easier to read. Okay? Generally, remember, make sure that you're Goldilocksing it. You're just right. So current balance, monthly interest, and also my current balance. I need to add my, what else? My monthly deposit. My monthly deposit. There we go. Do I have to separate that into 2 lines? Okay. Is there an argument for not doing that? I could go ahead and put it into 1 line instead. Right. Again, you're in the gray area. Is it better to separate every single operation out into its own line or not? Does that make it more readable or not? Right? You can have a healthy debate about that. I'll go ahead and leave it like this, though. Okay? All right. So I now actually need to print something. So printf. The way that I printed it on here was the month, to keep track of that, the balance, the monthly interest, and then the new balance. So those are going to be percent %D, right? Followed by a dollar figure here, percent whatever 0.2f. Why do I only go with, percent, there we go, with a dollar sign in front of it? Why do I only go out to 2 decimal places here? It's money, right? At least US dollars, you cannot get a half a penny anymore or anything like that. Now, in real financial situations, you can, of course, have a very, very small amount of money if you buy stock. If you can buy 5.000001 shares of Microsoft or something like that, and you are able to do that on certain exchanges. But for a savings account, that's way simpler. No, right? There's another dollar figure. There's another dollar figure, and then I'll end the line. Okay. The things that I want to print are the month, which is the variable I, then the balance, which is my current balance, and then the monthly interest rate interest that I've earned, and then the new balance. Uh-oh. Am I going to get a difference in printing the current balance twice here? Nope. All right, so we might have to come back, but let's iteratively test this thing. Let's see what it looks like so far. Does it at least compile and run and not get in an infinite loop here? Let me jump up to the top here, and great, I've already got a ready-made test case here. Is it correct? The first month, month 1, was $1,104.17. Yep. The next month we said it was $4.60, and then the last month you said it was $5.04. It all looks right to me. Right? Okay. But the problem is that the old balance and the new balance are exactly the same. That's not what I wanted. Right? So I could go back to the drawing board in here and say, well, I don't want to print the current balance just to print the new balance because, you know, it's this is repeated. This figure is going to this figure would end up down here anyway. If in the example that I have here, this figure would end up down here anyway. But let's figure it out anyway. How do I make sure that I don't lose the old balance before I print the new balance? I've got the old balance and the new balance, and I want to print them both. How do I go about doing that? I could split it up into 2 print statements. Right? I could print it out. I could print out this part before I print out this part. I don't like splitting up statements like that, though. Is there another way? Yeah, you're not paying by the variable, are you? Create another variable. Right? Create the old balance. Right? Before you change the current balance, double old balance is equal to the current balance. Right? Now, this is declared inside the loop. Does it exist after the loop? No, because of scoping rules. Remember scope? A variable is declared in a block of code. It only exists for that block of code. I would not be able to come down here and say that old balance is now equal to $42.50. Right? It doesn't know what old balance is because it only exists as far as, in fact, it doesn't even exist for this whole loop. It only exists from line 14 down to line 16, and then it goes away. And a new variable is created for each iteration. So that looks good. And instead of printing out the current balance, we'll print out the old balance, the monthly interest, and then the current balance. And let's see if that works. I'll run it again. There we go. OK, $1,000. There's the old balance. There's the new balance. The new balance is repeated down here. We add 460 to it, and we get this. Right? So it looks like it works to me, but it actually doesn't. Right, if you go if you go line by line here, and if you extend this what you did by hand here, you'll find eventually that after 10 years, you're probably going to be off by a few pennies. Why are we off by a few pennies? Say what? Rounding. Right? We never rounded anything, right, did we? Like we did over here, $4.17, and then some other loose change, right? But we just added it all, right? Eventually, we're going that error, that not rounding off those lower order digits. It's going to start compounding until we get extra money, right? And this has been exploited even in Hollywood movies, right? One of the Bibles of movie, or one of the core movies of anybody in IT is not The Office. Dang it. Office Space, right? If you've never seen Office Space, you need to watch Office Space, right? It's a good primer for actually working in an office. Office Space, where they write a program to take advantage of all those rounding errors and take that extra money that would have been rounded off anyway and put it into their own savings account. It actually was done. In fact, in the movie, they refer to it. It was done in the 70s by some hackers, and they got caught, of course. It was also the plot of one of the terrible Superman movies, et cetera, et cetera. So it's not a new idea here, but it's an idea that we have to take care of here. So when I compute my monthly interest, I'm going to go ahead and round that. Right? Let's give myself some more room here. All right, round the monthly interest, and the round function is where? In the math library. I think it's in the math library. It is. Okay. It just wasn't complaining about it. Did that fix it? Oh, we're certainly rounding now. What are we rounding to? To the whole number, right? Because that's what the round function does. $4.17, that gets rounded to $4. I'm sure the bank would love this, but are we going? Is that what we want to do? No, I want my pennies. All right. So we don't want to round to the nearest whole number. Instead, I can go ahead and RTM. I can go ahead and open up the manual, start reading. Is there a round to cents function in the math library? Well, is there? Is there a round to cents? Say what? Round to decimal? I don't think that there is a. I don't think there is, but we can certainly make one, and that's what we'll be doing when we start talking about functions. But how can I solve the problem temporarily? Yeah, go ahead. Okay. What'll that do? That'll shift everything over, right? That'll shift those 17 cents over. And now if I round, where am I rounding to? The whole cents. Is that the end, though? What do I need to do after it? Divide by 100 to get it back. Right? So in the, I'll go ahead and I'll take your advice here and multiply by 100. I don't need 100.0. And I also don't need 100.0 over here because round does return a double, I believe. So I'll go ahead and leave it like this and see if it works. And there we go. Right? And did anybody bother to look and see what the snapshot was? You can go back in the video if you want. Did we actually have $17,175.26? I think I'm pretty sure that after 10 years, the original, if we did not round here, would have actually been different. So let me just test really. 1717526. All right, let's go ahead and undo those changes. Undo. There we go. And let's try it again. Yeah, okay. Undo. All right, fine. All right. Run it. And no, we were off by 2 cents, right? Now, you're off by 2 cents. That might not be that's nothing as if you're just playing around with a stupid program in a programming class. But if you're working for a major corporation and you forget a decimal place somewhere, yep. In fact, there have been market crashes. In fact, do you know if the market crashes more than 500 points, they now have federal regulations that they have to close, right? This prevents an absolute market collapse. There have been things like this in the past where there have been auto trading programs that screwed up. There was a decimal place off somewhere, and they just started selling, selling really, really low, driving down the price, and of course, program talking to program, talking to program, talking to program. It all was just automated. One mistake in the system caused 50 other mistakes to be made, and millions of dollars, at least on paper, were lost in an instant. Now, nobody's going to be crying for those billionaires and millionaires because in the morning it'll be fixed and everybody's balance will be back up. And who cares if you lose $1 million if you've got $1 billion? But you also have to remember that many people's personal fortunes are in 401ks, and 401ks are invested in the market. Anything that hurts the market does hurt normal, regular people. Right? All right. So redo, round, times 100, and divide by 100. Oh, and I lost an E. There we go. All right, that looks pretty good. We can, of course, go ahead and change things out. What if your monthly deposit is $200 instead? Well, you'd expect, 200 times 120, you'd expect about $20,000 more at the end. That's about there, yeah, something like that. So you can play around with that, play around with a bunch of inputs and see if it makes sense. Of course, can you have a negative balance? You can, but then what's going to happen? Then the bank's going to be calling and the overdrafts and stuff like that. Can you have a negative interest rate? They charge you to hold the money in the bank. Okay. All right, change banks then. Monthly deposit, well, you could have a negative monthly deposit. That means that you're taking out, and eventually you're going to have negative money, right? So you can model a whole bunch of stuff. The point here is that you may need to do basic error checking, and that is required, and we've tried to get you to do that on all of your programs up to this point since we introduced conditionals. This thing is not allowed to be negative. A lot of you on your first homework that you went full, I think that people looked up like the world height record and the world weight record, and they made conditional checks on the other end, which we were not expecting at all. That if you were more than 1,200 pounds, then we're not going to go ahead and calculate your BMR or something. That was not necessary, but great. You were thinking about the other end as well. Right? All right. I'll go ahead and cut and paste this into the notes so that you have it when I post it later. And we have about 20 minutes left here. So I did want to motivate and at least start the next topic, which is functions. Because it was, there was a bookend to that that we're dovetailing into this now. Because what did I want? I wanted a round descent function. There was no round descent function. There's just a round function. So what I want to do is I want to be able to write my own functions that potentially use other functions, and I'll have function calling function calling function so that I don't have to write all my own code all the time, right? And that's one of the purposes of writing functions in any programming language. First of all, what is a function? A function is a reusable unit of code that may take inputs, right? Or it might take just one input. That's why I put inputs, or no input at all, and may, I'll emphasize may, produce an output. Right? Input, output. This is exactly what a program does anyway. You give inputs to a program, and it produces outputs. And we call these functions because of math functions. For 1 second here, let me go ahead and switch back over to the doc cam. There we go. Tell me what a function looks like in math. Okay. Well, yeah, there you go. F of x. Right? F of x is going to be a function. For example, give me a function. Give me one function. Oh, okay, I like x squared. Right? So what does that look like? Looks like a parabola. I should have hit the origin, but no points for art today. All right. Say what? Okay, +1. All right. Yeah. All right. So what do we call this? What do we call this line? X-axis. Right. What is x? X is the input to the function. Right. What is this line? This is the y-axis. This is why we sometimes write it y is equal to f of x, or y is equal to x squared. Right. This is the output of the function. Right? And if you want to look at it as with respect to just one input and one output, you are looking at mapping an input to an output value over here. Right? Now, is this a function? The circle. Is that a function? No. Why? What's that test that you can run? The vertical line test. Right? Why does the vertical line test fail to show that this is a function? There are two outputs. Right? You can't have two outputs in math. Likewise, in programming, you can't, at least in C, you cannot have two outputs. There's only ever one, at most, one output. Right? Now you can have multiple inputs. Here we've got one input. What kind of a function would have no inputs? Here's one. Yeah, constant functions, right? This is a function, right? It passes your vertical line test. It doesn't pass the horizontal line test, but that's something different. This is just a constant function. It doesn't take inputs, and regardless of the input, so therefore, regardless of the input, it's always producing the same output. You can have these in programming as well. Likewise, I'm running out. Here we go. That's not sensitive. So here's another example. F of x, y. Right? That's still a function in math, right? But what does it look like now? Now it's in x, y, and z. Right? Now you're taking two values, right? An x value and a y value, and then you're mapping it up to some z value. Right? So still only one output, but you can have 1, 2 inputs. You can have 3 inputs. You can have 4 inputs. You can have 5 inputs. What's the problem with having 3 inputs, though, in math? You can't draw it anymore, right? Why can't you draw it anymore? If I have 3 inputs, what is that going to be? The input is in 3 dimensions, but to graph it, you'd have to go up to 4 dimensions. Right? And unfortunately, we're just simple 3-dimensional beings. We don't know what 4 dimensions look like. Actually, we do know what, and many of you should know what 4 dimensions looks like now because of both Marvel movies and Interstellar. What does 4 dimensions look like now? Yeah, what is this called? Captain Marvel, or not Captain, Captain America or whatever. Right? That's called the Tesseract. That's a 4-dimensional cube projected down onto 3-dimensional space, projected down onto 2-dimensional space so that I can actually draw it. Right? So the takeaway to this is that math functions and coding functions operate almost exactly the same way. You have inputs, and then you have at most 1 output. Of course, you could have 0 outputs. So they're very similar to math functions. And I'm not going to redraw that in Markdown here, but you are already familiar with several functions. You've already been using several functions. Give me an example. Sine, or like that. Cosine, tangent, yeah. Just give me one trigonometric function. One is enough. What other kinds of functions have you used? Round, okay. What else? Printf. Printf is a function, right? It doesn't produce any it produces output as far as printing stuff, and it does actually technically return a variable, but we haven't been using it, right? So you can ignore the output. Right? What else? Scanf. Right? But what's the number one function, the very first function that you always use in any programming? The main is also a function, right? Etc. So you've been using functions up to this point, but now we're going to start writing our own functions. Why do you want to write your own functions? Or why do you want to use functions to begin with? Functions facilitate code reuse. You don't want to reinvent the wheel. You don't copy pasta. That is, cut and paste. You don't want to reinvent the wheel. There we go. Instead, you want to just take, if you're using this chunk of code in 1, 2, 3, 4 places in your program, take that chunk of code, put it into this box. Now reuse that box over and over again so that you're not taking this piece of code and cutting and pasting it at 5 different places and propagating errors throughout your code. If there's an error in the original and you start copy pasting, then the error propagates and all of them are incorrect. Right? So you don't want to have to reinvent the wheel. It also facilitates what's called procedural abstraction. Right? And before I define that, how does the sine function work? You should all know that from yesterday now. Or at least one possibility. It's a sum of a bunch of things. What's that sum called? It's a Taylor series, right? So yeah, trigonometric functions have Taylor series. Maybe that's how it's done. Now I'll throw you for a loop here. What about the square root function? How does it work? Okay, somewhere in between. Okay, now I'll guess again until it gets down to where it goes. That's kind of how, that's basically how it works. Or that's one way of working. There's also a Taylor series for it. But before I asked that question, did you care? No, you just used it. Exactly. And that should have been the answer, actually. Right? How does the square root function work? Who cares? I don't need to develop the square root function. I just need to use it to compute these this quadratic equation over here, right? And that's what procedural abstraction is. It relieves you of the need of having to worry about those details. Functions allow you to ignore implementation details of how a certain block of code works. You can just use it. Right? You don't have to worry about it. Now, if you're actually implementing the function, then you have to worry about it. But once you've implemented it, you've packaged it up into this function, and you've put it into your own personal library, now you don't have to worry about that anymore. That's a cognitive load off of your brain. You don't have to worry about how it works or why it works or what. You just know I can put stuff into it, and I can take stuff out of it, and it works. Right? That means that you don't have to think about it anymore. Functions, here's another term, encapsulate functionality into reusable, abstract blocks of code, right? Or units of code, I should say. Right? And this is where a lot of times we get the term unit testing. Once you've written a function, it's kind of what we like to call a black box. You don't not only do you not care about how the function works inside, you shouldn't know how it works inside. It's a black box. You put stuff into this black box and stuff comes out of it. It's black because it's opaque. You can't see it. It's not transparent. You can't open it up and look at it. Kind of like the web grader. It's a black box tester. You can't open it up and look and see what the inputs it's giving and how it's working. Instead, you just run your program, and the inputs are fed into it, and the output is fed out of it. So it's perfect. It's a perfect unit of code for unit testing because it's just one thing now, and you can test it by giving it an input, 3 inputs here, and looking and observing the output. So it's a perfect unit to test things. Standard libraries, and external libraries provide useful libraries, functions that have a lot of testing, debugging, and optimization behind them. If you don't use functions, if you don't use standard library functions or pull in a library to do the work for you, not only are you repeating all the work because you have to rewrite all the code anyway, but you're ignoring all of the person hours that went into that, all of the debugging hours, all the testing, right? If you roll, we call it rolling your own for various reasons, but we call it, if you write your own square root function, you're rolling your own square root function. And have you tested it? Well, maybe, maybe not, but you certainly haven't tested it as much as the standard library square root function. And you'll never be able to compare to something that has existed for 40 years and has thousands and thousands of hours proven behind it. So if there's a choice, always use a standard library function. Right? Don't throw those resources away. Right? Or don't ignore those resources, I should say. And it also feeds into an overall problem-solving strategy. All right. There we go. So, engineers. Most of you are engineers or are aspiring engineers. Problem-solving. What's the first question you ask yourself when you're posed with a problem? Here's a problem. You need to solve it. What's the first question you ask yourself? What do we know? Like, we need to understand the problem. After you understand the problem, then what do you ask? Is there what? There you go. Has it already been solved? Right? Has somebody already built something that I can use off the shelf to solve this problem? Right? You want to track snowmobiles, and you want to track whether or not their plow is down on a certain street or something like this. This is a real project. I'm not just making this up. This is many years ago, though. And you want to track whether or not their plow is down on a certain street so that you can report this information to municipal authorities and say that, yeah, that street will be cleared within an hour or something like that, right? Do you start by building your own chips and for the hardware? Do you start by building your own stuff and reproducing everything from scratch? No. You use some off-the-shelf components. Has somebody already built a small portable computer that would help me with this? Has somebody already built an altimeter or whatever they're called that would be able to calculate whether or not it's level or not level? And so you take these off-the-shelf components and you put them together, you glue them together, and now you've got the product that you're looking for, right? You always ask yourself, is there some solution that already exists? Well, coding is the same way. You need to solve a problem. The first question you should ask yourself is there a function that does this task for me already? Right? Or, failing that, is there a function that can help me partially solve this task? Right? And that's exactly what we just did with the rounding function. I asked myself, is there a round to sense function? No. But is there something that can help me do that? Yeah, the round function. All I need to do is shift it by 100, multiply it by 100, and then call the round function, and then shift it down by 100. If I took that idea of shifting it up by 100, and then dividing it by 100, calling round, and then dividing it by 100, and I put that into my own function, and I called that function round to sense, guess what? I've got a function now that rounds to sense, and I can reuse that all over the place if I want to. Right? So that's the beauty of creating functions. It feeds into everything that we've been doing up to this point, problem-solving tasks, code reuse so that you don't have to redo everything all the time. Functions in C. As with variables, functions have to be declared before you can use them. Right? The way that you do this in C, you declare and I'll put this in quotation marks here, declare a function by creating what's called a prototype. A prototype is nothing more. Yeah, I spelled it prototype. Yeah, I spelled it correctly. Is simply a declaration that defines a function's what's called signature. Declaration defines, there we go, a function's signature. So in real life, what is a signature? If I sign something, it's my way of identifying something, right? It's a way of identifying something or somebody. A signature in this case is the name of the function. Oops, I didn't close that off. There we go. The name of the function, also called its identifier. Right? For example, what's the identifier? What's the name of the square root function? SQRT, right? The list of its inputs, it's called parameters or arguments. And the type of variable that the function outputs or returns. And this is a key word, so I'll go ahead, return. There we go. We've seen this before with main, right? It returns a certain value. How have we been declaring main? What kind of variable does main return? An integer. What type of variable does square root return? What do you think? Square root returns a double, right? It doesn't return a character, right? It doesn't say yes, right? Right? There's something like that. It returns a number, a floating point number, a double, right? So here, let's go ahead and give you an example, right? Let's go ahead and do that round to sense function, right? So the first part is round to sense. That'll return what kind of a return? I'll call it round to sense. There we go. What kind of a variable should it return? We were returning $4.17. So what kind of variable is that? A double. That's how we define the return values type. double. Now, does it take any inputs? It's just like math, by the way. Functions, the functions that you've been using up to this point, have parentheses. Why do you think they did it like that? Because they borrowed the idea from math. And how does math do it? They write parentheses, f of x, by putting parentheses there. Right? So what kind of inputs does it take? Does it take no inputs? Or should it take no inputs? I want to give it, here's $4.17 and 4.1755555, and I want 4.18 back, right? So what kind of variable does it take as an argument or a parameter? Double, right? And well, I'll just call it x, right? Value or currency or something like that. I'll just call it x because I'm not that creative. I don't know what else to call it. Money, money, amount. There we go. Whatever. I'll go ahead and go with amount. That sounds better than x. Right. That is a function prototype. It has the return type, then followed by a space, and then the name of the function. And then in parentheses, it has a list of the variables that you provide as input. Now, if there are 2 inputs, then you delimit them by a comma, and we'll do that later. If there are 3 inputs, then of course you'd have 3 and then 2 commas there. Right? And what does it end with? Semicolon, just like a variable declaration. Int x, what do you end that line with? A semicolon. Okay. So, some syntax notes here. That prototypes end with a semicolon. Right? And documentation is usually written above a prototype. Right? So here's where some real documentation comes in. Up to this point, the only documentation that we've been expecting is you documenting a program up with your header. From now on, anytime you write a function, that function needs to be documented. I'm going to go ahead and use doc-style commenting here. Again, you don't have to, but you should get into the habit of doing something like this. The doc-style comment documentation is going to be /*, followed by vertical slashes all the way. Come on, it's not letting me do. There we go. And there we go. There we go. As many as you need, vertically aligned here, and then a */ to end it. Okay. Now, all we're going to. No, I don't want anything. All right, there we go. I'm going to document this function by telling you what it does. This function rounds the given amount to the nearest 1/100th. Is that how you spell it? I.e., the nearest cent. Right? And returns the value. Right? And then, of course, we don't need this much vertical space. I'll put in a little bit of vertical space there. Right? And you if you use full doc-style comments, you would also annotate everything else up, and it's a whole deal and a whole thing. Usually you rely on an IDE to generate that code, and then you just fill in the blanks for it. I'm not going to go that far. Right? But you definitely do need this kind of documentation here. If there were exceptions, for example, if you didn't support negative numbers, you could put that into the documentation and say that if given a negative number, we return not a number. And a whole bunch of other things that you can do. And if you do it in doc-style comments like this, then you can usually run a tool to generate documentation in, say, PDF format and an HTML format to publish on a web page, or in a RTM, right? Let's see, C math library. Right. This is documentation. Right? It tells where's the square root? Square root. There we go. This is documentation. Here's the prototype. This is the return type. This is the name of the function. This is what it takes. The return value returns the square root of x. And if there are any exceptions to this, this is not the real documentation, damn it. What about negative numbers? All right, fine. I'll go to the command line with our last minute here. If I go to the man page for square root, I get a whole bunch of other things. For example, let's see, where is it? Synopsis. Here, special values. You can put that into your documentation, that if you give me a square root of x returns not a number if you give me a negative number. And so you can put that kind of stuff into your documentation, and that's where you should put it, on the prototype. Once you have a prototype, then later on you define what the function actually does, which is what we'll do on Monday.